Hello, everyone. Welcome to This Week on Mars. My name is Ian Hewitt. I'm with Gupta College of Science at Coastal Carolina University. This is our weekly podcast talking about things on related to Mars and specifically related to the Mars 2020 Perseverance rover. So this week we'd like to continue our saga of talking about the helicopter on Mars. So last week we talked a lot about the Ingenuity helicopter and described the technology and some and the reasons it's designed the way it is. But we said we would talk more when it would actually fly. And so now that they've done some testing and flying, we're going to talk about that this week. It's really exciting. So when we last left Ingenuity, and last week in the video, the plan was to unlock and do a low-speed rotor spin test, then do a high-speed rotor spin test. Both of those take place on the ground, so you don't actually fly when you do that, but they're just tests to make sure everything's working properly. And then do the first flight test, and then do a second flight test. And that was the plan. Now, for those of you that were following the news last week, it didn't quite go as smoothly as they'd hoped, but in the end, it all worked out all right. Spoiler alert. So let's go ahead and talk a little bit about that. So first, let's talk about the first Martian airstrip, or airport, if you will, and it's named Wright Field after Orville and Wilbur Wright, of course, who made the first airplane flight here on Earth. So in order to honor that, NASA has named their airfield Wright Field. So basically, what they have is you can see the little mark on here. There's a mark, uh, a little dot here that's actually where the rover actually landed and originally set down. And so they've kind of marked out a relatively flat spot which they're going to call their flight zone. So there's a landing spot where the Perseverance rover, when we talked about last week, we talked about how it deployed the rover by dropping its belly pan and then dropping the rover and driving away. So it dropped the rover right in this little square here in the center of the airfield, and then it sort of got a flight zone marked out or planned out. Kind of in a kind of oblong shape here. So that's and you can see the bar here, it says that length is about 10 meters. So you can see it's a fairly decent size. It's, probably the size of a football field. So there's plenty of room just in case, you need a little bit of room, right? So another tie to the first Earth flight is the Wright Flyer. Okay, the Wright Flyer, which actually flew for the first time in North Carolina. Orville and Wilbur Wright took a short flight a little over 100 years ago. And there's a tie to that, another tie, because what they did is, and this is a picture from NASA and JPL, is they actually took the original Wright Flyer was made of wood and fabric. So the wings are not metal, they're actually made of fabric. So they actually got a small piece of the original fabric for the flight, for the craft that took the first flight, and they actually uh, attach that to Ingenuity, right? So it was a little bit of an honor for the first Earth flight. The first flight on another planet, Mars, will have some of the fabric from that very first Earth for that very first Earth craft. So that's actually pretty kind of a neat little honor that they did for the Wright brothers. So how this is going to go down is you see here's another look at Wright Field, and you can see where the helicopter is deployed. So again, it's in that little square, and you've got this about football field sized area that's considered the flight location. You definitely you don't want the rover inside the flight location because you don't want to be dodging around the rover. But at the same time, you want the rover is going to kind of overlook everything and give us all the data just in case there's an issue. You actually want to get good video of it and see what's going on. So the rover actually kind of went up and climbed up just a little bit. It's not too much of a rise, but you can see it's gone to this place they now call the Van Zyl Overlook, and it's about 40 meters, so that's about 120 feet away from the helicopter, and basically the rover will sit there pretty much for most of the helicopter testing, which will take about 30 days, and we'll watch the helicopter do its various maneuvers and report back. So the first step was to do a slow speed rotor spin test. This is only about 50 RPMs. It would never be able to fly at 50 RPMs, but basically this just involves unlocking the rotors and making sure they spin freely. I have a little bit of video from that. Let's go ahead and kick that in. There's no sound, but you can see it's a very slow speed. This occurred on April 9th, and you can see that everything seems to go pretty well. And so the rotors actually do spin. The video is not it's not super high def video coming off because the rover is really not set up to capture that. So, but it does capture a pretty good view of that. So the next test is the high-speed rotor spin test. So again, here you're going to speed them up to something on the order of 2,400 RPMs, which is where you get flight speed. Now, in this test, you're not taking the rover off. You just want to make sure it spins at full speed so it can take off. And so they're actually going to run this video. This is a little bit different. It looks like it's spinning. It doesn't look like it's spinning quite as fast because they actually used a little bit different mode to take the video, but it is spinning. And so what happened? They ran this on April 10th, and they were running this and trying to get the rotors up to speed. And you can see they get faster and faster, but then there's a problem. Because there was a problem with this test. The command sequence, the command sequence that was controlling the test, it stopped due to a Watchdog Timer expiration. So this is a software issue, right? So that's what canceled the original flight, which was supposed to fly earlier. So all of a sudden they have a problem, right? So let's talk a little bit about that. We talk about a Watchdog Timer expiration. What does that mean? What's the problem? What happens? Well, the thing about it is when you have real-time systems, and when you talk about the helicopter or the rover, you're talking about a real-time system, and that's a little bit different than say like your Mac or your PC, in that they tend to have a lot of watchdog timers. And so the way a watchdog timer works, it's usually implemented in hardware, and you've got your computer that's doing what it needs to do. And basically what it does is it sets, when it starts doing whatever task it's doing, it sets a watchdog timer. So basically it sets this piece of hardware that it will set some value with some time. Could be 2 seconds, could be a couple of milliseconds, however long that everything should take, you set it. And so what happens is that timer will then start ticking down, ticking down, ticking down, ticking down. Now, when your computer actually finishes the task, it usually goes and resets the watchdog timer, no problem. But what happens is if for some reason, if there's something going on, like there's a software glitch or a hardware problem, or for some reason it's not getting done what it needs to done, and that timer expires, then it actually sends a message back to the computer and calls a special routine that says, hey, there's a problem because they were supposed to get back to me and they didn't get back to me. So you need to take a corrective action. And these timers can have multiple stages. A lot of times they have 3, right? And so then what it'll do is it'll say that the first timer will set another timer. And then when that second timer goes off, it'll get another corrective action. And then that will set a third timer. And the third timer, when it goes off, is going to say, well, I've told you to fix this twice now, and obviously there must be a really bad problem. And basically it will go ahead and reset and restart the whole system. So this is actually pretty common in real-time systems. It's a way to sort of kind of guard. So the reason why do this, of course, is you want to catch software bugs that you don't catch before bad things happen. It's one thing to have a software bug on your PC or your Mac, because when you get a software bug there, it may not be critical. I mean, you may not have to turn off the Netflix or the YouTube you're watching and have to restart it. But the thing is, when in these real-time systems like these rovers, bad things can happen. Like if you have a software bug and the rover's driving, you don't want it to drive off a cliff. So basically, before bad things happen, that watchdog timer would go off on the rover and say, stop, something's wrong. You need to reset yourself, right? Same thing with hardware faults. If you've got a hardware problem, again, you want to catch it before bad things happen. And that's really what real-time systems are all about, or these embedded real-time systems, is that the difference is they've got special routines that will watch the time very carefully, and they know about how long things should take. And if something takes longer than that, they know there's a problem, and they're going to trigger corrective action. And that's really what happened with the Mars helicopter. The computer was supposed to go from pre-flight mode into flight mode over a certain amount of time. And what happened was things didn't happen as fast as it expected. And so rather than just say keep going and then we'll try to take off, but everything's not ready and we crash, the Ingenuity helicopter actually shut the test down, shut the rotors down, and went into like a safe mode. It says, okay, I'm going to be safe, right? You need to tell me whatever you told me to do was not correct, and I don't want bad things to happen, so you need to give me new instructions. And the rover works the same way. So that's really what happened here on this. So how to fix software on Mars? Of course, that leads to a really interesting engineering problem. NASA actually considered multiple approaches. The thing is, they can test all these on Earth, here on Earth, because all these missions, the Perseverance rover and the helicopter, they have duplicate flight hardware, the same hardware that's on Mars. They have it here on Earth, and they actually have like what they call a Mars yard, and it's actually like a simulated Martian terrain. And they can actually go ahead and test everything here that they want to do. So they had two plans. Plan one was just to change the sequence of commands to add some steps. The advantage is this is easy to do, right? You can just send it a different set of commands, and that the Watchdog timer probably would get reset and not go off, right? The risk, of course, is it may not exactly address the problem. The second plan is actually a little riskier, and it's to actually update the software and create a new version and basically update it, which it has the capability of doing it. It's a little slow because it has to go be uploaded from Earth and uploaded to the rover and then uploaded to Ingenuity. But you can do it. It has the ability to do that. The advantage is that's a guaranteed fix of the issue because you're going to fix the issue when you send it the new software. The risk is you're changing software that's been stable and tested for 2 years and hasn't any change for 2 years. So do you introduce any other bugs? So there was a lot of debate over that. And so basically what they ended up doing was they ended up going with plan one. And the good news is this actually fixed the problem. And they were able to actually get through the test with no problem. So now that we've actually got through the test, we can talk about flights. So here's the first flight plan. It's a very simple test. You want to spin up the rotors, again, without the timeout. And then I notice I'm sort of blocking part of the text here, so I'll have to move my screen next time. You spin up the rotors, and then you want to transition the computer to flight mode, and then you want to take off, and you climb about 10 feet in the Martian air. So really just about 10 feet high. And then you want it to hover, then rotate 90 degrees, and then you're going to want it to land. Now, it's a pretty simple flight plan. So so hold on. And it's a pretty simple flight plan. And again, because you're still in a test mode. The key thing to remember, and we talked about this last week, is there's no real detailed remote control, right? And this is because of the light speed limitations, right? It takes time for commands to go to Mars and for you to see the results. And right now that's on the order of about 10 minutes or so. So it's too much lag for remote control. So the thing is, it's got to be pretty autonomous. Once you tell Ingenuity, you give Ingenuity some general commands like take off and hover, and it's got to do that on its own. It's the flight computers have to manage all that, and you're just kind of watching. So once it's flying, it's really on its own because you can't do the remote control. And if you want to learn more about that, you can look at last week's video. So here's the first flight on another planet, first flight of Mars. So it's very exciting. Let's actually watch. This is the video from the Perseverance rover. And what you'll see is it will spin up and then go to high speed mode. And now you'll see it will raise up about 10 feet. And then if you look carefully, you'll actually notice it actually rotate. There it goes. Rotate 90 degrees. And it's hovering pretty steadily and doing a good job. It's actually flying. It's not bouncing around. Not too much anyway, but you don't expect it to be perfect because it's a very lightweight craft. And then it goes and sets itself down no problem. So very exciting. This is the first time we've ever flown anything on another planet, and you actually got to see that. So very exciting. Here's a picture from the onboard camera because it does have onboard cameras. So this is its shadow on Mars. So this is a picture taken from the downward-looking camera while it was in flight. So the good news is that went so well, NASA actually did a second flight, and so I've got part of the video of that flight here, and you can see it's already in the air at this point. Kind of making a few turns, and basically just kind of staying pretty steady and staying up a little bit longer. This was a more extended sequence of turns. There wasn't a lot of, it didn't go a lot of distance. It didn't actually zoom around Mars. It's just a longer second flight test. And that's about all the video I have of that. So the good news is that went very well. And here's a camera shot from the second onboard camera image. It kind of looks like the first one a little bit, but you're in the same spot, so you would expect that. So what's next? Well, there's about another 21-day window left for more tests. They had about 30-day window for helicopter testing. And why do they have a limited testing? Perseverance is going to be on Mars a long time. And that's true, but you don't want it sitting at the Van Zyl Overlook all the time. You actually want it actually doing work. So they dedicated about 30 days to actually focus on this helicopter test. So now what they're doing is this second flight test was actually this morning when we were recording the video, so Thursday, April 22nd. So the NASA engineers are actually meeting to actually get more sophisticated flight plans, because what they didn't do is they didn't actually fly around that whole airfield area. And that's going to be the next plan. The next flight tests they're actually going to be flying around and do a lot more sophisticated flight plans. And they're working on the details of that, and we'll talk about those when they actually get those out and they actually make some of the flights. So it's very, very exciting stuff. So stay tuned, and we'll learn more about the Mars helicopter. I hope you enjoyed it. Everybody have a great week, and we'll talk to you next week.